So next let's talk about how we're going to, let's derive the estimators that we're going to use for beta 0 and beta 1. So those are those beta 0 and beta 1. So let's just write it down. Deriving OLS estimators. It's easier if we can maybe visually see what we're trying to do. So y equals beta 0 plus beta 1 x1 plus u. And if you remember, we said that these two things were parameters. So if you remember from the review of stats last module, we're coming up with estimators that take our sample, apply some rule, and give us a value for these parameters. And we wanted certain properties of those estimators. So that's what we're talking about doing now. How do we come up with estimators for beta 0 and beta 1? What are our estimators? What are our rules that we use for any given sample? Okay. So let's, to do this, we need a sample and an estimator. And an estimator. So like some kind of rule. So we talked about 3 different kind of approaches to estimation. So we need kind of one of these approaches that we're going to kind of implement to get estimators for these parameters. So let's first think about writing out our regression this way. So notice I added this subscript I. So it's like the observation subscript. Observation subscript. I think I need to change this pen. Hopefully it still comes through. Observation subscript. So each person in our sample, remember there's n people in our sample. This is the ith person's value for y. So if I equals 3, then this value, so y subscript 3 is the third person's, let's say, wages or something like that. So notice that with both of our variables, y and x, there's an I subscript. And every person in our sample is going to have some level of u. I mean, we don't get to see u, it's unobserved, but some level of u. Everyone has their own. Okay, so let's kind of think about our least squared approach to coming up with an estimator, and we can derive the estimators for beta 0 and beta 1 here. All right, so we have our regression function here with these 1i. Sometimes I forget the 1, but we're only kind of dealing with 1x right now. So just assume there's kind of a 1 attached to this x if I forget. Just like in class. All right, so let's rearrange this just a little bit. So think about ui being the difference, the error term here being the difference between, let's try to erase that with my finger. Oops, and this should obviously be a minus if we don't have it in brackets. So this error term is the difference between these observed values, and then kind of we're subtracting what our beta 0 and our beta 1 times x1i. And so what our estimators kind of try to do is minimize the sum over our entire sample of kind of the distance, how far off we are in terms of the actual observed value and kind of what our model is predicting for that level of x in terms of the value of y. So that's like the idea here. Trying to minimize, so we're squaring it, so every value is positive, so we don't have negative and positives cancel out. Another way of doing that is with absolute values, right? But maybe those derivatives are a little too hard for us. So we want to minimize this squared distance between our kind of observed values of y and what our kind of, think about as like predicted values of y is going to be. So that's kind of what we're thinking about. So let's exactly plug in you could hear the pen drop maybe, plug in ui equals yi minus beta 0 minus beta 1 x1i. Just from here, right? I mean, that's essentially, I'm just rewriting that. Okay, so let's plug that in. Now where'd my other pen go? My blue pen? Over here. Okay, so we're gonna minimize the sum over our, from I equals 1 to n, so this is our whole sample here, our sample size is n, yi minus beta 0 minus beta 1 x1i squared. We're just plugging that in there. And so this is what we're trying, like this is our least squared estimator. Now, we're minimizing, but we got to minimize over something. Well, what do we get to pick? We get to pick what our estimators are, right? We get to pick beta 0 and beta 1. So maybe this is our estimator here. Our estimator is W, and it's whatever beta 0 and beta 1 we get that minimize this square difference between our observed values and kind of what our guess is or our estimate is. So that's the idea. Well, you might have seen minimization and maximization problems in like intermediate micro or macro. Well, when in doubt, we take the derivative, right? So we have two derivatives to take here, one with respect to each of them. Let's use a different color. Maybe I have one. Okay, so let's take the derivative with respect to beta 0 and then the derivative with respect to beta 1. So we're trying to minimize this, so we're going to take the derivative and we're going to set it equal to 0. So let's take the derivative of this function with respect to beta 0. So the derivative of the inside is minus 1. Right? And then we need the derivative of the outside. Well, this comes down and we have everything still, right? So minus 1 times, oops, we don't need another minus there, 2 times the sum yi minus beta 0 minus beta 1 x1i. And we know that equals 0 at its minimum. Derivative of the inside, derivative of the outside. Chain rule, right? The only thing that might be kind of confusing is those sums, but you'll get used to them. Okay, now we can take the derivative with respect to beta 1. So again, we have a minus there, so it's minus 1. But we have this x1i still attached. So again, we're going to have this minus 1. But then we have the sum. Ooh, that was a bad one. Should put I equals 1 to n here too. The sum. Again, now we have that extra x1i here. It looks a bit different than the one above because we have this x1i attached. So this is the derivative kind of the inside. We're halfway down the whole thing now. Derivative of the inside. And then derivative of the outside, which is the same as before. So again, we can just put a little 2 there. That's that exponent coming down. And then we have that this whole term again here. Oops, minus beta 1 x1i equals 0. Well, pretty easily we hopefully realize we can just get rid of these front two, all the constants kind of outside of the sum, because we can just divide both sides by -2, right? And we get rid of those. So now we have two equations here. And two unknowns. with beta 0 and beta 1. Now I'm going to go back and do something really quickly. This is going to be somewhat, I mean, it's important to understand kind of what's happening. So these beta zeros, remember, were the true values. But now we're coming up with an estimator. They're not representing the true values anymore. So as soon as we take the derivative, we should start putting hats on these betas. And the hats are kind of indicating that they're estimates or estimators, right? Without a hat, it's like the true value. So whenever you don't see a hat on a beta, it means it's the true value. These are not the true values. These are what we're coming up with as our kind of guess, I mean, educated guess through statistics, of what these values are. So that's why there's these hats on them here. All right, so let's go back to that other first order condition where we took the derivative with respect to beta hat 1. We had this extra x1i at the front. Beta hat 0, beta hat 1, x1i, and this was our first order condition. So what we're going to do now is, well, we're going to plug in that beta hat 0 equals y bar minus beta hat 1 x1 bar, so we just solve for. And what we're trying to do otherwise is to isolate, oops, not beta hat 0, we're just trying to isolate beta hat 1. So we're going to plug it in, what we got for beta hat 0, and then we're going to isolate for beta hat 1. So the first thing we can do is think about, well, let's just plug it in first. It'll be easier to see. And that should turn into a plus, minus is a plus, minus beta hat 1, x1i equals 0. Right, so this was a minus here, but we're subtracting beta hat 0, so it turned into a plus right there. Okay, so like I was trying to say above, but maybe got a bit messy, we're trying to isolate for this beta hat 1. That's what we're trying to solve for now. So notice it's a common factor of these last two terms. And maybe we could start to think about kind of dividing this between terms that have beta hat 1 in it and terms that don't. Okay, so let's just do that. So the first sum we're going to have are these first couple terms. So let's just leave those together since they don't have a beta hat 1 involved. And then we're going to think about another sum. So let's common factor this beta hat 1 out. We still have this being multiplied in, so x1i. Then we have x1 bar minus x1i equals 0. So between these two lines, we're just kind of dividing the sum right here. We're kind of keeping everything there together, and we're kind of keeping the terms that have this beta 1 hat common factor. And we can think about now moving this to the other side, right? Because then we can think about actually isolating this beta hat 1. So we're going to move this to the other side, and when we do that, we're just going to flip these two x's. So now it's going to become x1i minus x1 bar, right? Because that's what we're doing as we move it over. So instead of changing this to a minus, as we bring it over here, we're actually just going to flip this, what's in the brackets, if that makes sense. And then equals beta hat 1, the sum x1i minus x1 bar. And we're almost there. Now we just need to isolate for this. So I'm just going to move it to the other side. Beta hat 1 equals the sum. I'm just going to write it a little bit differently here. Forgot this. But oftentimes, so that's perfectly fine. This is one way of expressing the slope parameter or the slope estimator for our OLS. But a lot of times you're going to see it written a little bit differently, and mathematically it's equivalent. It might seem a little bit crazy, but it is. So these are mathematically the same thing, these two things. Might seem crazy, you can do the math. Basically what it's saying is that x1i minus x bar times x1i is the same as x1i minus x bar squared, and the same for the numerator. You can try that mathematically and you'll see they're the same, just using rules of sums. Alright, so now we've solved for our least squares estimators for simple regression. We have beta at 0, so what our estimator for the intercept for this, for the regressions are going to be, is we're taking the sample mean and we're subtracting the slope parameter times the sample average for x1. So the sample average for y minus whatever this estimator is, we're going to write down below, times the sample average for x1. And again, we solved just for this. I'm going to write it in that other way that we were talking about. X1i minus x bar, I guess we're putting a 1 there, and then the same thing down here squared. So these are our estimators. So these are the rules that we're going to apply to our sample to come up with parameter estimates for the intercept and the slope.